Assalamualaikum and hi. Okay, today I want to continue our lesson for the FET DC biasing. Now we want to use different transistor, which is E-MOSFET. Okay, E-MOSFET, for the E-MOSFET DC biasing, it has a slightly different in circuit configuration. Although the fixed bias, self bias and minimal bias configuration can be applied to E-MOSFET, but there are only two biasing that is very popular for this kind of MOSFET. Those two most popular bias configuration are feedback bias configuration and also voltage divider bias configuration. Let's take a look for the feedback bias configuration. The term feedback means that for the gate terminal is fed or supplied by the VD. Okay, in this configuration, it seems that RS has been removed, resulting in VS equal to 0. So no RS, and there is a feedback here where the RG is located here. Okay. As the situation for this one, when in DC analysis, okay, IG equal to 0 still apply. Therefore, the resistor RG will be ignored, resulting in the drain and gate terminal to have the same voltage. It means that, okay, previously we has RG here, but in theory, the IG is actually equal to 0. So it means that it only is like a short circuit. So the resistor here can be removed. Okay, the resistor can be removed, and it become only short circuit. Okay. When it's short circuit, okay, you see that this is terminal D, and we always measure the VD here. VD, and here is VG. Okay, because of there is no voltage difference, okay, between G and D, okay, because it's already short circuit, right? So here no voltage difference between G and D. So we say that voltage VD now is equal with the voltage VG. Okay. So if I measure VD now, this VD and VG value is same, even though there is a VGS here and also VDS here. Okay, so remember that for the feedback bias configuration, VG equal to VD. Okay, let's take a look the example. Determine IDQ and VGSQ for this circuit. So here ID, okay, this is the characteristic of E-MOSFET. You must remember this one. Okay, it's different from the JFET and D-MOSFET, where here it use ID on, VGS on, and VGSTH. VGSTH is equal to VT, or threshold voltage. Okay, so from this characteristic, you must keep in your mind, okay, the graph is like this. Okay, this is the ID, this is the VGS. So here is VT. VT is where the voltage, where the current will start to increase before, if VGS less than VT, so the transistor is actually off. Okay, if VGS greater than VT, transistor is on. So this area is the transistor will be on. Okay, and the ID is keep increasing. Okay. Okay. To calculate the IDQ and VGSQ using the mathematical method, and again, first you need to draw the DC equivalent circuit. This is very important because it helps you to see the component clearly together with the relevant voltage and also current. Like this circuit, as we know, has a RG here. However, because of IG equal to 0, and it become a short circuit. Therefore, the voltage for VD and VG will be same. Okay, so another one is here, because there is no RS, so we can say that VS equal to 0. Next, we calculate for the equation for the circuit. Okay, so equation for the circuit is VGS. Okay, always remember, equation for the circuit is VGS. Right. For this one, it has slightly different from the other circuit like self-bias, fixed bias, and voltage divider. We need to find VG. Okay, so from this one, we know that VG is equal with the VD. Okay, we can use from this side to get VD. Okay, so I start with the VD first. Means I want to calculate the VD here. Then I choose loop from this part. Okay, I change this VDD into like this, and the loop is from here to here. Okay, so I get, if the KVL is negative VDD, okay, if I choose like this, plus ID RD and plus VD equal to 0. Then rearrange the equation, become like this: VD equal to VDD minus ID RD, and insert its value here. And then let me see the VG. Okay, VG is here. Okay, VG is here. So for the VG, we can use the same loop also from here, okay, to here. Okay, because now this is only a short circuit, and the result here, you will get the same equation as a VD. VDD minus ID RD. Okay, let me see this one. Negative VDD plus ID RD plus VG. So we get this equation. See, these two equation has the same value. Okay, therefore we can say VG equal to VD. Okay, now we already get the VG value. We take a look for the S. Okay, VS. To find VS here, VS is 0 because there is no RS. Therefore, the final answer for the VGS is VG only. Okay, VG is 12 minus 2K ID. Okay, next, okay, we find the equation for the device. Okay, so we are not using Shockley equation. Okay, not using Shockley equation. Okay, then for the E-MOSFET, there is a one important parameter which is K. Okay, and this is the formula. K equal to ID on divided by VGS on minus VT squared. Okay, insert the information given in the circuit. ID on is 6 milli, VGS on is 8 minus VT, and you get this answer. Please remember the unit for the K is ampere over volt squared. Okay, once you get the K value, insert this K value into the equation for the E-MOSFET. General equation is ID equal to K VGS minus VT squared. Okay, so insert this value K, and this means that VGS must be greater than T for a transistor to on. Okay, so transistor will be on. Then once you get ID equation, okay, insert the VGS here, VGS equation into the ID, because we have VGS here. Okay, we call it from the previous equation. So when you insert the VGS here, this is the VGS. Okay, then expand the equation, so you get ID equal to 0.24 milli multiplied with 9 minus 2K ID squared. Then you solve this equation, right, until you get like this. Okay, remember, this is equal to ID. It's still equal to ID. 19.44 milli minus 8.64 ID plus 960 ID squared. And here is ID. So remember to bring the ID over here, which means it become minus 1. So negative 8.64 minus 1 ID, it become negative 0.64 ID. And this is the equation. Okay, and here this is A, this is B, this is C. Then solve the equation, okay, manually or using your calculator. Okay, using this formula. Okay, and then you will get ID, two values for ID, 7.25 milliampere, and second ID is a 2.79 milliampere. Alright, so now which one is the IDQ? Okay, can you get can you guess which one is the IDQ? The first one or the second one? Because the for the E-MOSFET, there is no IDSS that we can compare for the ID. This is why, because you need to remember that, the graph, the current keep increasing. Therefore, there is no limitation for the current. So, we need to insert these two value into VGS equation. Okay, due to E-MOSFET doesn't have limitation for saturation current, the value of ID have to be checked with the circuit equation VGS to make sure which one is the true value of ID. Okay, so go back to the VGS equation and insert the ID for each one. For the first ID, okay, I calculate here, I get negative 2.5 volt. Second ID is 6.42 volt. Then we compare with VT, not VP. Remember that E-MOSFET doesn't have VP. Okay, it has VT. So VT that we use, that is used for this device, is 3, right? So it is in positive VGS or VT. So we take this one, okay, because this 2.5V is here, okay, negative 2.5 is here. This is out of the area, okay, the area to on is here. This is off and this is on, okay. So this is the VGSQ and this is the IDQ.